Okay, in the earlier lecture we just looked at how two phase commit and the three phase commit protocols work. What we are going to look at in this lecture is the concurrency control protocols for distributed systems and how these concurrency control protocols can be integrated with the commit protocols. In the first few minutes what we are going to look at it is how the two phase locking protocol can be integrated with the two phase commit protocol for the distributed systems. Now, what we have is basically in the two phase locking there are two phases of execution which we have seen earlier. There is basically a growing phase in which the transactions acquire the locks, and then there is an actual point where they start releasing the locks, and the rule here is that in terms of time, this is a time axis. Now, in terms of the time axis, what you are looking at here is a particular phase where this is basically called the growing phase, where the transaction is acquiring the locks, and this is the shrinking phase where it is releasing the locks. Now, one of the conditions is this is basically called the lock point. So, if you have actually released one lock, you can't ask for more locks. That is how basically it ensures that transactions always execute in a serializable order. Now, this is basically the transaction execution points. For example, this is a start point and this is the end point. Now, if you release a lock for a transaction, then somebody else in between can read the values of this data items that you have actually modified. For example, assume that even before you have finished, you released a lock on a data item, which actually means that somebody else can now read the value of that data item, right. Assume that there is a data item X, okay, and now you actually have acquired a write lock on X during the growing phase and then release this lock during the shrinking phase. Now, it is possible that when you have actually modified the value of X, let us say X is now modified from earlier value is 20, now it got modified itself to 30. Now, during this phase when you release the lock, somebody can acquire this lock, which means that they can read the value of X which you have modified before you have actually committed, which means that if you now want to abort, then the transactions which read these values earlier all have to abort. This will result in a cascading aborts. If you allow transactions to read the values, other transactions to read the values of the data items before the transaction is actually committed. Okay. So, in general this execution of the two phase locking is not correct, because you cannot release the locks, okay, before you have actually committed. So, what modification that we are going to get when you integrate two phase locking with commit is, you basically will acquire all the locks, you will come to the commit point, but your lock point, and then you are going to keep these locks till the end of the transaction execution plus the commit phase. Only after the commit phase, after you have committed, that means this is the point where you have actually commit point, you are going to release your locks in terms of the time scale. This is the number of locks that you have. Okay. So, the number of locks are actually increasing with time. The transaction is actually started at some point here and it started executing. Now, it acquired all the locks it required. This is the point where it actually reached, it required all the all the locks, then it continued execution, somewhere here it actually finished execution. That means, this is the execution phase. Okay. Now, after the execution is over, the commit protocol is going to be started now, because then it has to decide to commit. Then this is the zone in which the commit protocol gets executed, and after the commit protocol is executed, the transaction actually finishes execution, then the locks are all released at the same time. But if you release the locks earlier, this will result in the isolation property being sacrificed and other transactions able to read the values of still uncommitted modified values of this transaction. So, you are not going to release the locks as shown in the earlier diagram, but this integrates both the locking and the commit protocols together, and after execution is over you actually run the commit protocol and then release your locks. Okay. This is how the two phase locking is integrated with the commit protocol. Now, if you want to see in the distributed setting how the distributed two phase locking will work, it is actually a simple extension of the two phase locking, because what you are going to now see is distributed 2PL plus its integration with the two phase commit. Two phase commit is for distributed transactions, because commit protocols make sense only in the case when you have multiple nodes where your transaction is executing. Otherwise, there is no question of involving a two phase commit there, because you are actually finding out if the participants can all commit their transaction. If there is only one single node, that node knows already it reaches the commit phase, all that it has to now decide is whether it is committing the transaction or not. Now, in the case of distributed 2PL, how we are going to execute the transaction is, you basically have a coordinator which we have shown earlier. This is basically the root transaction, okay, and the root transaction has actually spawned the sub transactions, which actually means that you have actually a TR1 here and there is a TR2 here. Now, the TR1 actually executes a 2PL, which actually means that it acquires all the locks that it actually needs, and this other transaction also acquires all the locks it needs in terms of the 2PL. Okay. Now, each one of them, when they reach the commit phase, have to decide whether they are committing or not committing. When the actual commit message has been taken by the coordinator, that is the time they will commit and release their locks. Okay. Imagine that there is actually a data item x on which this transaction is operating, T1 is operating, there is a data item y on which transaction 2 is operating. Okay. Now, T1 will acquire locks on x, T2 will acquire locks on y, they finish their part of the execution. Now, at the end of the execution, each one is going to decide whether it is going to commit its part of the transaction. That is where the two phase commit will start execution, or the two phase commit protocol is run to figure out whether both of these transactions are willing to commit. Now, based on that, based on the commit protocol outcome, they will commit the transaction and then release the locks. Now, the important thing what we discussed in the earlier lecture is what happens when failure occurs, and then what is the problem of blocking. Now, assume that T2 gets blocked, transaction 2 gets blocked, which actually means that it is not going to release the locks it has acquired till such time it actually made a decision on committing or abort. The locks are not released till the commit protocol has actually finished, which means that other transactions which try to acquire locks now on these data items will be blocked from acquiring the locks. So, basically blocking in that sense is not good, for the simple reason that the resources are blocked. In this case data items are blocked from access by other nodes. What I am going to show is a slight extension of this two phase locking protocol. The basic two phase locking is used on the actual nodes, that means the each node will run a two phase locking for the data items it is actually accessing, but this two phase locking is used for local data items. We are not further looking at TR1 accessing a data item that is remote to that particular node. Okay. And if you basically want to look at that model, you will realize that there could be problems of applying two phase locking, where each sub transaction could access both local data items as well as remote data items. Assume for example, you have a root transaction here, this is the root transaction, and then you basically have two sub transactions T1 and T2 here spawned on two different nodes N1 and N2. Now, let us say N1 has actually data items X, Y, and let us say this is having P and Q. Okay. Now, assume that T1 actually wants to acquire a lock on X, a read lock on X, and then also wants to acquire a read lock on, let us say, P, remote lock on the. Now, which means that it has to send its lock request to the other node N2. Okay. Now, for example, this is already locked by T2, you have actually T2 has actually acquired a write lock already on P. Now, unless you understand T1 and T2 are part of the same transaction, T2 will be blocking T1 from acquiring a lock on P. Normally what you do in the distributed transaction model is to access the local data items only, you will actually spawn a sub transaction there. You will not actually allow a sub transaction running on one node to acquire locks on a, basically if any time you require to access a data item on a different node, you spawn an agent there which is basically a sub transaction of your main transaction. Okay. If you basically want to provide this extension, there is an extension that is possible for the simple two phase locking, which is called the nested 2PL. The extension of nested 2PL takes care of the extension of the 2PL to the scenario of distributed transactions, where all these transactions, sub transactions are seen as children of the root transaction. Now, any lock request that basically is needed by the transaction is, the lock request is sent to the root node, and it is basically the root node which acquires the locks on behalf of the children node. This could mean that, for example, the T2 actually wants a lock on P2, P actually, this lock is acquired, okay, in terms of the root node and then inherited by the T2. Okay. Now, when T2 actually finishes, this lock is not released, but then given back to the root node. Okay. Now, if T1 actually wants the lock, it gets it from the root node. So, all data items, the locks for the data items are with the root node. Now, any time you actually require a lock, you are making a request to your root node and acquiring the lock, and when you actually finish, you are releasing the lock to the root. The root acquires these locks back. Okay. Now, if these are actually the same children of the same transaction, the locks are held by the root. So, it basically does not conflict. The two transactions, child transactions of the same root node does not basically conflict with each other. the conflict is relieved because they are children of the same node. Okay. Now, the way this execution is going to be done in the nested 2PL is, there are two kinds of models that one can think of. One is called the open nested 2PL and the other is a closed nested 2PL. Now, in the case of the open nested 2PL, you are actually assuming that in the tree structure that you have, these are all actually sub transactions that are possible. Okay. Now, this is basically the root, you can take this as T1 and this as T2, and there are actually two sub transactions for T1 and there are actually two more for T21 and T22. So, you basically have a tree in terms of showing how the transactions are spawned. Okay. Now, it is possible for only the child nodes to acquire the locks in terms of actually operating on the data items. Okay. That means, T1 will never do anything except saying that there are T11 and T12 which basically access or modify the data items. That means, only the leaf nodes, one possibility is to say only the leaf nodes are allowed to modify or process the data items, and if you allow these intermediate nodes also to do this processing, then it becomes an open nested 2PL. And if you put the restriction saying that only leaf nodes can do the processing on the data items, it becomes a closed nested 2PL. Okay. Typically, what the nested transactions are meaning here is, T1 consists of T11 and T12, and it is possible for T11 to further go down and have T11, okay, and then this can be, you can further have T112. This is a sub transaction of T11, you further have a nesting there. So, you can actually make this nesting further nesting, which means that you can always divide a main transaction into a sub transaction. Okay. Now, in terms of an open nested transaction, it is possible to actually convert an open nested transaction model into a closed nested transaction model, because if there is a processing being done at T1, you can typically make that, for example, this can be now here spawned separately as a sub transaction of T1 dash, which means that the processing is never done at the intermediate nodes. If there is a processing involved, you spawn a sub transaction to do it. Okay. That means, in terms of the root, the other than the leaf nodes, everybody else actually is spawning sub transactions, and whatever the sub transactions do, that result is being aggregated at the higher nodes. They do not do any processing by themselves. Okay. A simple extension of nested 2PL to nested 2PL requires that whatever locks are acquired by the children for doing processing are passed on to the parent when they finish execution of the transaction. Okay. And it is easy to see why nested 2PL will obey the serializability condition. Okay. All that has nested 2PL has is that the children never release the locks, but they are inherited by the parent when the transaction finishes. Okay. Now, it is possible for another child to acquire these locks from its parent. That means, when you need a lock, you have to first see whether your parent has the lock, then you are going to get the lock from your parent. Okay, you are inheriting from the parent the lock. Now, we assume that all the locks are with the parent. So, the only way you can acquire a lock is by making a request to your parent. When you actually finish your execution, you are returning the lock back to your parent. Okay. Now, we can see why this simple nested 2PL will ensure serializability by looking at intuitively what is happening here. Now, if you basically see that there are two branches of the tree and there is a lock acquired by any of these children here, there is now an inherent serializability at the higher level, because unless this, let me put in terms of simple tree structure nodes 1, 2, 3, okay, 4, 5, 6, 7. Now, you can see that the inherent order in which this execution can proceed is, if 3 requires a lock or 6 requires a lock that is currently held by any of the other nodes, the only way it can be obtained is through its parent, which actually means that unless 2 finishes, one cannot acquire the lock. That means, at the higher level the execution is always proceeds in terms of this tree, the nodes finishing, one node which is earlier in the tree finishes and later the other node can finish, otherwise there is no way that node can finish, right. So, inherently the tree structure will be ordering the way the transactions are executed and inherently provides a serializability condition. Okay. Now, you can say that that means the only execution sequence that is possible in this particular case is 4, after that 5, if there is a conflict, then 6 and 7. If there is no conflict, it is possible for this tree structure to be executed, for example, where okay, the leaf nodes are all. Okay. So, the same tree structure that we saw earlier, it is possible that I can have a different kind of an execution, where if there is no conflict, because if there is no conflict, it does not really matter how 6 and 7 are actually executed. If there is a conflict, that means if 5 is asking for a lock on data item x and 6 is also asking for the data item x, this will not be possible, because this lock would have been held by this node. Unless it finishes execution, this would not have happened, and hence this will be prevented. Okay. So, you can see in a simple case, a nested 2PL is an extension of a simple 2PL, where a transaction actually spawns a sub transaction, and now that sub transaction can further spawn other sub transactions, and then each sub transaction, when it finishes, gives its locks to its parent, and that is the only way the execution can proceed, and that inherently ensures the serializability requirement. This is an extension of simple 2PL to nested 2PL for distributed systems. This one possible model. We have also seen a number of actually time stamping schemes as part of our earlier discussion on transaction models. Now, it is worth actually seeing what exactly happens with time stamping schemes in the distributed scenario. Okay. Now, what we have is the basic time stamping scheme, which shows how exactly transactions can be executed by having a basic timestamp being given to both the transaction as well as to the data items. Okay. Now, in the basic time stamping scheme, every transaction is given is given a timestamp at the beginning of the execution. Okay. Now, this timestamp could be just the logical clock value that we saw in the distributed systems, which means that this is a local clock that is maintained by the distributed system, which in effect means that this is to be either a synchronized clock or some kind of logical synchronization happens between these clocks, such that the timestamp reflects a total order among the transactions that are actually executed in the distributed system. One way to do this is the last 2 bits, least significant bits are part of the each node, and the higher bit is actually a synchronized bit with the other clocks, the clocks of the other nodes. Okay. So, it is possible for you to give a timestamp for each of the transactions originating in each of the nodes of the distributed system. Now, if you assume that every transaction entering the distributed system can be executed on any node of the distributed system. So, this timestamp corresponds to the logical time that we saw in terms of the different nodes synchronizing their logical clocks. Okay. One extension is a simple case of the mutual exclusion algorithm that we had implemented in the case of Lampport's clocks. The same scheme is applicable here, except that instead of this being a mutual exclusion, it is going to be now a read lock or a write lock that you acquire on the data items. That means, in effect, this is equal to the timestamps being used for writing on the data items or reading on the data items. Now, different nodes will decide the order in which they can access these data items by using the timestamp value. Now, in the basic timestamping scheme, what we are essentially doing is we are actually giving the timestamp at the start of the execution of the transaction. Now, as the transaction starts executing, you are actually looking at its read set and you are seeing its write set, and then you are deciding in terms of the read set and the write set what are the timestamps of these data items, and making sure that the transactions are executed in terms of the timestamp order. Now, we assume that every read and write data items in the database have been given timestamp values. For example, let us take a simple case of actually looking at a data item X, which is in the database. Now, each data item will have 2 timestamps corresponding to it. One is the read timestamp, that means this gives the, this is basically the read timestamp. What the read timestamp will give you is the value of the timestamp the highest value of the timestamp of the transaction that has read X. That means, it tells which is the highest timestamp transaction that has read its value. Okay. Now, similarly, we will have one of write timestamp X, which tells correspondingly the write timestamp of the transaction. Okay. This is basically the write timestamp. The explanation for the write stamp is similar, except that instead of what we had put there as read, now this is the highest value of the transaction which has actually written on the data item X. Okay. The value of the timestamp of the transaction that has written on X. Okay. Now, the use of the read timestamp and the write timestamp is, for serializability you always allow the transactions to only do in terms of increasing values. That means, if there is a new transaction that comes in whose timestamp is lower than the write timestamp, and if you want to allow that to read now the value, you obviously will have problems, right. For example, if the write timestamp of the data item is greater than the transaction timestamp, then you should prevent it from reading the X value. In that case, basically you need to abort the transaction and then ask it to come again with a higher timestamp, so that you are preventing the access to the data items in terms of, always the data items should be accessed by the transactions in terms of increasing timestamp. If you ensure that, you are automatically achieving a serializability condition, right. Now, in a simple way, in a distributed setting, you are going to extend the basic timestamp to a distributed transaction model by just ensuring that these timestamps are generated in a consistent way by the nodes of the distributed system. If each one of them generate the timestamps, the transaction timestamps are generated in a global way, even when the data items are distributed, you are still ensuring that globally all the reads and writes are ordered according to the timestamps of the transaction. Since the timestamps of the transactions are generated in a consistent way in the global system, we are essentially ensuring a serializability order for your transactions coming in the distributed execution. Okay. Right. So, basically that is an extension of the basic time stamping scheme to the distributed scenario. The extension is quite simple and straightforward again in this particular case, ensuring that the logical clocks of the distributed system are synchronized and executed properly as per that order. Now, one of the interesting extensions that one can see is a completely optimistic extension of the time stamping scheme, where the data is fully replicated on all the nodes, which means that now every node has the data items available locally. So, what you are going to do now is you are going to look at each node is going to send its read set and the write set to everybody, and now everybody can vote on the reads and the writes, and if whatever reads and writes you have an appropriate number of votes, then you will be able to make the modification, which means that the majority of the copies are always consistent and they always proceed in the same order as being done by the nodes. Let us look at that extension, and it is often called the optimistic time stamping scheme, and I will actually summarize the different time stamping schemes which I have done earlier with respect to the distributed scenario. The optimistic scheme is interesting extension, because what you have is here a fully replicated database. That means the data items are fully replicated on all the nodes. Now, take a simple case where there is a node n1 and there are 2 data items x and y, and take another node n2. What is going to happen now is it will also have x and y, which is essentially means that all that a transaction is going to do now is it is going to produce a a list of data items that it is willing to modify along with the transaction timestamp which it is trying to do. Okay. Now, what it is going to do now is it needs to send this information to all the other nodes, and the other nodes have to now say whether they are willing to accept this list that is sent by another node. That means, every transactions modifications what it has read and what it wants to modify will be sent to all the other nodes, and now those nodes can decide whether that update list is consistent as far as they are concerned. If they say yes, then if enough number of yes votes are come for a transaction, then obviously it can commit. If it does not get that, then it cannot basically commit, which means all the processing is always going to happen locally, but then you are going to send your read list and write list for voting to other nodes. Now, the other nodes can decide whether to vote yes or no on this particular data items. Let us take a little more detailed way and then see what really happens in this particular case and how the transaction execution is going to proceed. In this particular case, what you are going to see is, let us say I have a transaction T1 which started at let us say 10:20 here with respect to its timestamp. Now, it is basically trying to read x and write y. Okay. So, that means its read set consists of x data item and its basically write set consists of y. Okay. Now, it will modify whatever it wants to modify as far as this transaction is concerned, and produces this list for other transactions to vote. That means, it will communicate this list to node n1 saying that as far as this T1 is concerned, it is at time 10:20 it is modifying x and y, and that list is being sent to the other node. Now, we assume that there is basically a read timestamp on x which actually shows again what is the highest value of the transaction that are actually read x, and similarly the write transaction on y. Okay. Now, what you are going to see is, if this list is actually non conflicting as far as the other node is concerned, what we mean by non conflicting is basically there is a set of transactions which want to execute on the other node as well. Okay. Now, what you have to check on the other node is, before this modification is done, whether this modification is consistent as far as the other node is concerned, and the consistency criterion here is this x and y, whatever this transaction is trying to do now is later than whatever has been done already in the other node, which means that the corresponding RTS and WTS rules are applied on the other data item, and if it is consistent as far as that is concerned, then you are going to now vote saying that this is okay for me, because as far as I am concerned there is no conflict of these transactions for serializability. And if it is basically conflicting and these conditions does not hold good, the RTS or the WTS not being in the case of write transaction it has to be more than both RTS and WTS. In the case of a read transaction it is should be more than the write transaction WTS. So, in that sense we apply the consistency rules of RTS and WTS on the other node and decide whether this list is consistent. Now, that will not be enough, because this is only a proposal to modify, it is still not modified. There could be several such lists which would have come to me. Now, it is possible that there is a pending list with me and I have to actually compare these values with the pending list also. What is pending now with me? Okay. Now, let us say in the pending list none of it actually conflicts with what I have, then the rule is simple, then I will basically give a S vote for it. Okay. If there is in the pending list, if there is a conflict, which means that there is a list which came to me on which I have actually voted. Now, let us say there is a conflicting list with me and in the conflicting list I have voted an S for the conflicting list. Okay. Now, there are two things that can happen with the conflicting list. Let us say there is another transaction whose timestamp value, okay, is let us say there is it is 10:20 now, there is a conflicting T dash transaction here whose value is, let us say 10 o'clock, timestamp value is 10 o'clock, and let us say for this obviously I have voted an S earlier, that is why it is actually in my pending list. I have still not heard about this transaction. Okay. Now, one of the things that I can do in this particular case is, since I have already voted for T1 as S, T dash as S, the best thing I can do for T1 is say no, because it is conflicting and an earlier transaction I have already said yes. Okay. Since I have actually said yes to an earlier conflicting transaction, which means that this T dash is actually S for my case. Now, I actually have another transaction at T1 which is conflicting with my no already pending list. Let us say this X value it is trying to modify, okay, and when it is trying to modify this value of X, probably we should take a specific example here to make this little more clearer. Okay, basically what you are saying is this node N1 when it got a list, it is voting yes or no, right. Now, let us say there is basically let us take on node N1 the execution sequence and node N2 the execution sequence. It received a an update list of TR dash at 10 o'clock, and this is the list with X and Y, let us say it received saying that this is the update list. Now, it did not conflict with anything, so I actually voted S for it. It is still pending on my side because I have not heard the final decision on this, because the one who has actually sent me the list, if it gets enough yes votes, then it is going to commit it and send it finally to me as an update list. Then I will apply the updates to the actual, that is the time I update, but in this particular case this is pending list. I voted, but then the decision on this is still pending. Okay, there is no decision on this particular list. Now, what happened? There is another transaction T1 that came by and it is actually at 10:20, and then now if it is not conflicting with my pending list, there is no problem whatsoever, then I basically say yes. Now, let us say the one which came at 10:20 has a pending as a conflict with my pending list. Now, for that pending list I have actually voted an S. Okay. Now, one way for me to do is this 10:20 I will not reply immediately, but wait, I say okay till I get the decision on 10 o'clock, I am not going to vote on 10:20, which means that defer making a decision on, that is one possibility. That means this this list is not voted by me, I am not going to say yes for it. Okay. A no does not create problem, because a no has already been, I have actually said I am not willing to go with that pending list, okay, right. So, even if it conflicts, a no does not really bother you, because you have actually voted for some other reason, you are actually not willing to go with that transaction. Only when you said yes to something, then the current one is conflicting with it, then you have a problem now, whether will this create a problem or will this not create a problem, because based on that you have to make the decision. Okay. Now, assume a scenario where this is scenario 1. Okay. The scenario 2 could be same T1, the same T1 arrived at my node and now it is conflicting. Now, here also let us say I take the decision to defer making a decision in this case. Okay. Now, both scenario 1 and scenario 2 I defer, then imagine a possibility where none of the lists, the likelihood of getting a majority may not be there, because everybody is waiting for these lists to be voted, and there could be a case where none of them might receive, okay, enough votes and everybody is waiting for everybody else. Suddenly it looks like deferring voting on both the cases is not a good idea. Now, then the next case, which case I better vote no and which case I should better vote yes. Now, if you basically look at, I have already voted for the 10 o'clock case as yes. The best bet for me is that 10:20 can be deferred, because it is a later transaction. Okay. Suddenly if I have done something at 10 o'clock and if somebody is trying to come and do something at 10:20, it is still all right with me. Okay. But if it is actually 9:50, I better in this particular case vote as no, because I have already, this anyway will be, the only chance when it would have succeeded is the case where 10 o'clock did not get enough votes. In that particular case, the T1 has a chance, otherwise it does not have a chance, right. So, I can wait, I can always wait in both cases and decide only when I know about the fate of 10 o'clock transaction, because I voted for it, okay, and make any future things that are coming in till the pending list is clear, I will not make any other decision. But what happens in that case is the possibility of all the transactions waiting for each other, the pending lists, can result in nobody progressing. So, you better vote the case where it is 9:50 as, you vote for this as a no to avoid this confusion. Okay. Now, at the end of it, the majority votes, if a pending list actually gets a majority vote, that basically is sent as an update list for all the nodes. That means that list is now has to be updated by all the nodes with the, now the very fact that if any node has got enough votes and any pending list has got enough votes, okay, that becomes now a permanent right on it, and you can easily show that no two conflicting things can get, okay, both cannot get majority votes at the same time, because only one of them can win. If the two transactions are conflicting, only one of them in the end will be able to achieve the majority votes, and that is the one which will go through, and the other one is going to be restarted. Okay. If you basically look at it here, it is a completely optimistic scenario, because you are executing all the transactions and you are never checking the consistency before start execution of the transactions. What you are doing is you are executing the transaction, and at the end of it you are deciding by sending this updates to all the other nodes, you are seeing whether you can go through with this execution or not. Okay. So, this is typically the pessimistic scenario versus the optimistic scenario. Pessimistic, as we told earlier, the consistency check is made at the beginning of the execution, and then this is the begin. That means you actually do this checking. A locking would have ensured that the check is done in the beginning. Unless you acquire the locks, you are not proceeding on the execution. Okay. On the other hand, this check is made at the end, which actually means that you are actually executing the transaction fully and then applying the consistency check. Okay. Now, in that sense you are basically having the two spectrums. One is the locking based algorithms which fall in this spectrum, and then a fully optimistic time stamping schemes which fall in the scheme where the consistency check is only applied at the end of the execution sequence. Okay. A variety of models are possible as far as these transaction models are concerned based on the time stamping schemes. One of the most interesting scheme is to give what we have seen in the case of for example, visiting Tirupati temple. For example, you have the model where the band of time is given for you to go and then see the thing at that point of time. Basically you are scheduling transactions which can be executed in future. For example, you can say as far as T1 is concerned, you can give a band of time during which it can really execute, which means that when it starts executing you can say that this becomes the time before which if it commits it is alright for you. This is like telling if it comes at the gate at 10:20, this is not the start of the time, this is a virtual time of commit. So, as far as this transaction is concerned, if it commits at let us say 10 o'clock, it is fine with me. That means you are telling when it can commit, when it can actually finish its execution. So, you can actually give an order in which this is basically the end finish time, not at the start time that you are trying to schedule. You can actually do this at the end. For example, it is possible for you to tell even a band, let us say this transaction I can allow between 10 and 10:15 to execute, finish its execution. If I generate this band such that conflicting transactions will not finish in the same band, I have actually getting the serializability condition. For example, there could be another, for example, if the band that is given to these two transactions is different, if they are conflicting, let us say I give a band of 10:15 to 10:30 for this, it actually means that these suddenly they are not the serializability condition will not be violated here, because one is finishing at 10:15 and the other is finishing. So, I actually gave the band of time in which they can finish their execution, that is the other model that I can give. A completely different kind of a model is also possible, where you can say that I will basically do what is called only transaction timestamps, but not data timestamps. For example, all the schemes which I have seen so far have two kinds of timestamps. One is I am giving a timestamp to the transaction and I am giving the timestamp to the data item. You could do a scheme where all that you are going to do is, as the transaction is executing, you can give timestamps to different points of execution. For example, you can give start of the transaction, finish of the transaction, what is the time, and use that for actually doing the consistency check, but as long as one transaction finished before the other, if they are conflicting, and that you are able to ensure by looking at your clocks times that when things have actually happened, you are actually able to ensure the consistency condition. In a simple way, what we are talking about is, let us say T1 there is a start time and there is a finish time of T1, okay, and similarly T2 there is a start time and finish time, and these times are actually given by using a clock here. Okay. Now, as long as the conflicting transactions are all, as they are executing, these times are given, you can ensure that the serializability condition as far as the operations are concerned by making sure that the start and the finish times are properly synchronized as far as the transaction execution is concerned. By doing this, we actually do not need to maintain timestamps on the data items, that is a saving in terms of not needing to maintain the timestamps. Okay. A variety of schemes are possible, we have seen a couple of these schemes in this particular lecture.